Hello, my name is Javier Calderón Sánchez and I'm going to present this work that has been carried out with my colleagues at Universidad Politécnica de Madrid, Leo Miguel González and John Martínez Carrascal, titled Computational Scaling of SPH Simulations for Violent Sloshing Problems in Aircraft Fuel Tanks. This work is part of a broader project that is being developed by several European institutions that has to do with assessing the damping effects of sloshing on wing motions in order to minimize them, and the project is called SLOshing Wing Dynamics, or SLOD. This is the outline of the presentation. I will start by introducing what is the SLOD project, and that will serve us as a first step to talk about the problem description and how we can identify the main parameters of the problem that will become the inputs of the dimensional analysis that we performed. Using that as a base, the single-phase SPH model that was used for this problem will be described, emphasizing some particular but important aspects of the model. Then I will present how this model is coupled with a single degree of freedom mass spring damper system in order to obtain a complete fluid structure interaction problem. The two experimental campaigns that we present in the conference are then discussed. This is the numerical scaling and the influence of gravity. And finally, a set of conclusions is drafted. So, the aim of the SLOD project is to investigate how the use of fuel slosh might help to reduce design loads and motions on aircraft structures. This is a phenomenon particularly important at critical operations such as aircraft landing. Being able to quantify energy dissipation effects that are associated with liquid motion means that one can increase damping up to 50%, hence greatly reducing deformations and structural demands. You can find here a link to the project website as well as a video that will serve to illustrate the characteristics of the problem that is to be evaluated. As you can observe, very violent motion is attained, reaching up to 10 g accelerations. Fluid is highly fragmented and several impacts to the wall occur, meaning that, as you can imagine, the numerical computations are a challenge. In order to isolate complexities as much as possible, at UPM, a simplified version of the problem has been extensively tested. The box is released and a 1 degree of freedom decay test is carried out, reducing the structural modeling just to a mass spring damper system and measuring accelerations, motions and forces at the tank. However, the complex behavior of the fluid, as you can see, remains exactly the same. Once the problem is presented, dimensional analysis is carried out to extract the important variables. At the single-phase version, we neglect the effect of the gas phase, and the problem then reduces just to 8 non-dimensional relations. As you can see on the right figure, previous results from other numerical campaigns show the influence of some of these relationships. It is worth mentioning that all the previous campaigns were carried out at model scale. However, from experimental extrapolation, scaling effects might appear due to intrinsic limitations that are linked to the fact that the existing fluids have certain characteristics. In order to avoid them as much as possible, the use of a well-validated numerical tool can be extremely helpful. So in our problem, the relevant experimental parameters can be scaled according to the following laws, and also the resulting variables have a scale-dependent expression. Regarding the SPH model that is implemented, a weakly compressible SPH formulation is used. Dissipative terms are included both at continuity and momentum equations in order to stabilize the scheme, namely delta SPH and alpha term respectively. Additionally, a surface tension is added following the expression given by Morris, and the interactions with the wall are done with the boundary integrals formulation. It is important to note here that evaluating the normals correctly is critical in this problem. Have a look at the image in the slide that shows one of the jets that are created at different stages of the simulations. In order to achieve that, we follow the work by Peng and Sun in 2017, even though we are aware that this is an open topic that is gaining attention from SPH community, and we leave you here a more recent reference where the accurate modeling of surface tension is discussed. In order to couple the problem, making it dependent from the SPH solution, as we said, a 1 degree of freedom mass spring damper system is used. The K corresponds to the stiffness of the springs, and B0 and B1 are the damping constants. Both damping and stiffness constants are obtained from dry experiments. Forces are computed by SPH, and they do according to the following expressions. So, the two numerical campaigns that I am about to present have its base on the reference prototype test data that corresponds to water at 50% filling level. For more details of these prototype test data or these base data, you have the reference here below. And simulations in this work have been carried out with the fully free SPH software Aqua GPU SPH. Regarding scaling, this slide presents 4 figures corresponding to the main outputs of the simulation. This is the acceleration of the tank and the force and work done by SLOshing forces. As you can see, results are very similar for the 3 scales tested, so we can say that no scale effects are present and the scaling is working properly. Note that there are subtle differences in the forces, especially noticeable at first stages, that have an impact on acceleration and work done curves, both magnitudes that, as we say, depends on the force. Whereas for gravity, 3 different results have been tested. Gravity at Earth, denoted by G0, and 1 below and 1 over this reference value. Additionally, 3 different facilities have been tried, changing mainly the damping values in order to generate an underdamped and an overdamped system to analyze the effect of the experimental facilities. Then, 9 cases in total are presented. Figures show the acceleration decay curve and its corresponding envelope for the underdamped, the UPM, and the overdamped systems. Behavior is pretty similar for all the 3 facilities when comparing gravity value. We can say that reducing the value of gravity below the reference one has a little impact on the result. But this is not the point when it is increased. Having a greater gravity value, this is closer to the initial acceleration, plays a role on the fluid behavior that returns to rest faster, having a solid block-like behavior from previous stages, and hence reducing damping, which is linked to fragmentation and impacts. So, just to sum up, a fully coupled fluid structure interaction problem for vertical SLOshing has been implemented using a single-phase weakly compressible SPH model That includes surface tension. 2 numerical campaigns have been presented in order to assess the influence of scaling and gravity respectively. From gravity, we can say that it is relevant when values come close to the initial accelerations that force the fluid to return to rest faster. Scaling process is necessary to predict wing loading at full scale. Experiments might be limited at some point of the process, and there, numerical analysis becomes important to allow extrapolation. Having a well-validated tool becomes then crucial to obtain a successful result. Thanks for your attention.